Hello, my name is Kunhang Li. I am currently a master's student at the University of Tokyo. Today I would like to introduce our LREC-COLING 2024 work, Motion Generation from Fine-Grained Textual Descriptions. I finished this work with Professor Yan-Song Feng when I was a bachelor student at Peking University.
First, let me briefly introduce this task itself. Text to motion is to generate motion sequences from given textual descriptions. For example, this text, "A man slightly squats," is first passed into a generative text-to-motion model, which then generates its corresponding motion sequence shown here. However, the models from previous works can only deal with the sentences in the training set or similar sentences. In other words, previous works cannot deal with fine-grained text-to-motion. Our definition of fine-grained text-to-motion is twofold. The first fold is descriptive granularity, as shown here. Previous works' motion descriptions are only coarse-grained, like "a man slightly squats." However, we hope the text-to-motion model can also deal with fine-grained textual descriptions that reasonably and appropriately specify movements of relevant body parts. Correspondingly, we have the following expectations of the fine-grained descriptions. Firstly, they should be in time order. Secondly, they should specify spatial movements of relevant body parts. Thirdly, they should discard unnecessary details regarding muscle tension and human feelings. This is mainly to narrow our research scope. Lastly, they should conform to human body constraints. For this standard, a bad example is that the arms might have been raised in the previous sentences, but suddenly the following sentence assumes the arms rest on both sides of the body. From our perspective, the actual reason why previous models cannot deal with fine-grained descriptions is that they haven't gained the ability to generalize. Therefore, our second fold of fine-grained text-to-motion is generalizability. More specifically, generalizability is the ability to compose new motions in both spatial and temporal dimensions, which we call spatial and temporal compositionality. For example, suppose we have two basic motion descriptions. One is "a person slightly squats," and the other is "a man raises both arms above head." If the text-to-motion model has learned how to generate their motion sequences, then we hope the model can generate the motion sequence for "a man slightly squats with both arms raised above head." We call this spatial compositionality. Furthermore, suppose the model has learned to perform "a man walks" and "a man kicks with one leg." Then we hope the model can generate a motion performing "a man walks, then kicks with one leg." We call this temporal compositionality. Following our twofold fine-grained text-to-motion definition, our first question is, can we endow the text-to-motion model with the ability of expected compositionality on textual descriptions of various descriptive granularities? Meanwhile, since large language models are thought to acquire large amounts of common sense from texts, we have the second question. Do LLMs learn appropriate physical knowledge to help us with this problem? Our hypothesis is yes, and we take a straightforward approach. We aim to build the first fine-grained language motion dataset with the LLM and train a new text-to-motion model. So our approach is, firstly, we automatically build the first fine-grained language motion dataset, FineHumanML3D, using GPT 3.5 Turbo from an existing coarse-grained language motion dataset, HumanML3D. Secondly, we design a new text-to-motion model, FineMotionDiffuse, to better model fine-grained texts, inspired by the competitive text-to-motion model, MotionDiffuse. With this new model, we conduct training and evaluation. To build the fine-grained language motion dataset, we first conduct prompt engineering to find the optimal prompting strategies. In our two-shot prompt, we ask the LLM to add named step marks. Our pilot study shows that this trick helps better generation in time order. We explicitly ask the LLM not to specify anything related to muscles, which can be noisy for a skeleton-based human model. We also ask the LLM to convert the texts into pseudocodes. Our pilot study shows that this kind of pseudocode conversion improves the overall generation quality of the fine-grained descriptions in terms of our expectations. Of course, the automatically expanded fine-grained texts are not promised to perfectly align with their ground truth motions, so we conduct a human evaluation of 100 motions along with their new texts from the automatically built dataset FineHumanML3D. The number of perfect alignment is 30, while partial alignment is 68, while only 30 out of 100 motions are perfectly aligned with the fine-grained descriptions. Perfect alignment is an exceptionally high bar. In the majority of cases, partial alignment indeed captures the correct time order and relationships among core motions. In the large body of the partially aligned cases, issues like redundancy or deficiency are often trivial in nature. Substantive errors rarely occur outside complicated motions, such as juggling while doing the moonwalk. Therefore, despite the partial disagreement between fine-grained descriptions and golden motions, we aim to verify the usefulness and effectiveness of our data generation method through the performance of the downstream text-to-motion task. Furthermore, we propose a new text-to-motion model, Fine Motion Diffuse, which better models fine-grained texts. First, we extract texts of each step from the fine-grained description. Then we encode each step text in the original coarse-grained description using clip. The reason why we separately encode the text of each step from the fine-grained description is that clip can only accept up to 77 tokens, which appears too short for the whole fine-grained description. Each step embedding is acquired by averaging its encoded step text. We add positional embeddings to these step embeddings before passing through self-attention to model the order of consecutive steps. We call this mechanism step-aware self-attention. And then the token embeddings of the coarse-grained description and the step embeddings of the fine-grained description are fed into a cross-attention block, which we call fine-coarse cross-attention. The intuition is that we want to utilize both high-level instruction-like information from the coarse-grained description and the detailed information from the fine-grained description. Now we get the encoded text embeddings. Using these embeddings, we conduct training and inference. For easier comprehension of our results, we would like to show and compare cases of spatial and temporal compositionality from fine motion diffuse and motion diffuse. For all details of our quantitative and statistical qualitative evaluation, please refer to the paper. We also included animation videos of the important cases on our website. Here are cases of spatial compositionality. For fine motion diffuse, we input both coarse and fine-grained descriptions into it. Due to the space limits, we only put the coarse-grained descriptions here for demonstration. As you can see, we have two basic motions, squat and raise arms above head. Fine motion diffuse is able to compose the two basic motions spatially, resulting in squat while raising arms. To demonstrate fine motion diffuse advantages over motion diffuse, we also compare the results between the two models. We use the composite motion descriptions as input. Same as before, we only put the coarse-grained description here for demonstration. After inputting the fine-grained description into motion diffuse, the model fails to perform raising arms. Further, after inputting the coarse-grained description into motion diffuse, the model fails to start from the standing posture. And here are the cases of temporal compositionality. We have two basic motions performing walk and kick with one leg. and fine motion diffuse successfully stitch them temporally, that is, walk and then kick with one leg. However, motion diffuse fails in this composite motion in both fine and coarse-grained situations. For the fine-grained description, motion diffuse fails to kick. For the coarse-grained description, motion diffuse fails to walk first. To summarize our work, firstly, we find that the LLM has the appropriate knowledge to complement coarse-grained motion descriptions with satisfactory motion details. We further verify the feasibility of utilizing the LLM to automatically build a useful fine-grained language motion dataset, Fine Human ML3D. Secondly, we show that step-aware modeling and fine coarse cross-attention can make full use of both high-level instruction-like information from the coarse-grained descriptions and fine-grained body part-related information from the fine-grained descriptions. Correspondingly, we propose a new text-to-motion model, Fine Motion Diffuse. Thirdly, we find that our method helps the text-to-motion model learn the mappings from fine-grained descriptions to motion primitives, which leads to the emergence of spatial and temporal compositionality. Thank you very much for your attention. If you find this research interesting, please don't hesitate to check our website and the paper. See you!